There are times when we're doing triple integrals that it is convenient for us to use other coordinate systems, either because of the region that we're integrating over or because of the function that we're trying to integrate. We saw this with polar coordinates with double integrals, and we have similar kinds of things for triple integrals. So I want to talk about what are called cylindrical coordinates. We'll also do spherical coordinates in a couple days. But the idea is that you have your three-dimensional space here, your x, y, z axis. But instead of using x, y, and z to do each point, so here's a point in space, and I'll locate it here by dropping a perpendicular down to the xy plane so that you can see sort of where it is. Although rather than drawing x and y in there now, I'm going to connect a line to the origin. All right, so this is a point in the plane z equals 0. And from the positive x-axis, I'm going to look at this angle right here. I'm going to call it theta. And the distance away from the origin to this point is called r. Okay. So instead of x, y, and z, I'm going to have cylindrical coordinates of r, theta, and z. Okay. This is essentially polar coordinates in the xy plane, and tack a z coordinate on. So we can say that, for instance, this is the x coordinate, this is the y coordinate, this right angle. Then we can see the relationship between your old-fashioned rectangular coordinate system and now this thing called cylindrical coordinates, because what do we have here? Y divided by r is the sine of theta, so y is equal to r sine theta. Likewise, x divided by r is the cosine of theta, so x is equal to r cosine theta. And believe it or not, this may be tricky for you, but z is equal to z. So there is, if you know your cylindrical coordinates, you can calculate x, y, and z. Likewise, if you know x, y, and z, we want to be able to go the other way. Well, it's not quite so easy, because r squared is equal to x squared plus y squared. So choosing r as to be plus the square root or minus the square root, you have to know what quadrant you're in. Likewise, the tangent of the angle theta is y divided by x. So if you're trying to calculate theta, you're going to use an inverse tangent. But inverse tangent is only going to give you answers between minus pi over 2 and plus pi over 2. So if you're out in the second or third quadrant, you may need to adjust, or you may need to take r negative. And so this is, if you know x and y, how do you calculate r, or at least up to plus or minus x and y, how do you calculate theta, and how do you calculate z? Well, again, it may be hard for you to imagine, but z is actually just equal to z. So polar coordinates are not unique. That is, the points in the plane are not uniquely determined by their coordinates. There are many ways that you can describe the same set of point, the same point with different coordinates. Likewise here, because there's multiple ways of representing this point in polar coordinates, there'll be multiple ways of representing that point up there in cylindrical coordinates. Okay. Now sometimes this is a pain, sometimes this is really cool. We can do a lot of nifty things because of it. Okay. Some basic graphs, z, if you just have z equals a constant, that's still a plane parallel to the xy plane. So up here, wherever that constant is, that's the plane. If you have something like r equals a constant, well, r equals a constant down in the xy plane would be a circle, because there's no theta in here. But now that circle becomes a cylinder, because for any point on that cylinder, the r coordinate is the constant. It doesn't matter what theta and z are. So cylinders by just r equals a constant. If you had theta equals a constant, well, theta equals a constant would be a plane. So whatever that constant angle is, whatever that constant angle is, within the xy plane, you're describing a line, and it's not just a half line because r could be negative. So even though theta is looking in this direction, you could be backing up with negative r's. But then with z not being part of that equation, then z can be anything you want, and you're talking about a plane there parallel to actually contains the z-axis and goes off in the direction here of whatever theta is. So those are just some basic equations. We're going to look at graphs in general, either in class or in another one of these videos. But this is the basics. You're just talking polar coordinates in the xy plane, and then z for the third coordinate.